Alrighty, question 3b. The conducting wire AB is moved in a magnetic field as shown in the diagram below. Okay, so we see a whole bunch of crosses which represent a magnetic field, and they're going into the page, okay, or into your screen. Okay, so it gives you a whole bunch of data, and then it says, explain in detail what happens to the electrons, okay, electrons in the wire as the wire is moved in the magnetic field. In your answer, you should include ideas about the forces experienced by the electrons in the wire and the effect of the forces experienced by the electrons in the wire. So we're talking a whole bunch about forces on electrons in this magnetic field. Okay, so this question is actually made up of a whole bunch of different components, and we just need to quickly work through our way through them to be able to fully answer this question. Okay, here we have a magnetic field which is heading into the page, and I have an electron which has a velocity of 12 meters per second. And the question I just want to pose to you now is, what direction will this electron feel a force in? Alright, this is where we use the fourth right hand rule. Okay, so our thumb, okay, is the cause. You pull the thumb, you get slapped. Okay, so the cause of the force on the electron is the velocity. So that's our thumb. Okay, our fingers, because we've got lots of them, there's lots of crosses, that's the magnetic field line. Okay, and for a positive charge, it's a front slap, and because electrons are negative and they're a little bit sad, and we're a bit sad when we slap, we back slap for electrons. Okay, so a positive charge is a forward slap, and a negative charge is a back slap. So what does that mean for our electron? Well, it's moving down, so our thumb's going down, and our fingers are going into the page, and because it's negative, we back slap, okay, and so it experiences a force to the left, okay, and that force is a result of the magnetic field. Okay, so if we have a positive charge, same idea, okay, it's got a velocity going down, our thumb is pointing in the downwards direction. Okay, our fingers are into the page, and we like proper step this time, and it experiences a force to the right. Okay, and so a typical question might be, well, how much force does it feel? How do we work that out? Okay, if we head back to our formula sheet, we can see this force formula here, F equals B, VQ. B standing for magnetic field strength, Q standing for charge, V standing for velocity. Okay, and B in the question was 0.8 Tesla. The velocity in the question was 12 meters per second, and the charge on an electron is 1.6 times 10 to the negative 19. So the force, if this was just a free electron flying into a magnetic field, if we chucked that into the calculator, 0.8 times 12 times 1.6 would be 1.5 times 10 to the negative 18 newtons. Okay, a really small force. And it's exactly the same for a proton, but it would be in the opposite direction. So this question of an electron moving through a magnetic field of a particular velocity can be directly applied to question 3b. We have a conductor. It has to be a conductor because there has to be free electrons that can move, which is moving in a magnetic field of 0.8 Tesla, and it's 0.65 meters wide. Okay, we've got to ask, well, what's happening? Well, inside here is a whole bunch of electrons, and just like in the previous question, an electron's going, if it's moving downwards with a magnetic field which is heading into the page, it's going to experience a force to the left. Exactly the same here. Okay, we're going to get all of our negative charges at this end of the pipe, and we're going to get, as a result, all the positive charges at this end of the pipe. Okay, so that's an achieved answer. If you say that the electrons inside a conductor in a magnetic field experience a force, and that force is to the left, electrons to the left, and the absence of electrons or protons in inverted commas to the right, positive charges, then that's worth an achieve. To go a little bit further, we've got to ask, can we continue separating electrons forever? And why not, and what sort of makes a difference in that? And I suppose to begin answering that question, you've got to ask, well, what happens if we have a whole bunch of positive charges and a whole bunch of negative charges all separated by some sort of distance? What do we get? Well, I suppose that's quite similar to our electric field that we've been drawing in 1A, okay, which was draw the electric field. We got electric field lines which went from positive to negative. By having a separation of charge, by having electrons on one side and positive charges on the other side, we get this separation of charge which creates an electric field. Okay, and that's pretty easy. That's just like question 1A. But the typical sort of question that you'd normally be asked in an exam or something is something like this. There is a free electron with a charge of 1.6 times 10 to the negative 19 on the negative plate of the following electric field. So we've got an electron over here. Okay, how much force does it experience? Well, how do we know that? If we come over to our formula sheet, we can see that F equals EQ, where F is force, E is electric field strength, and Q is charge. Well, how do we work out electric field strength? Electric field strength is voltage divided by distance. So if we were crazy, we could actually replace this E with that E over there. So we could say that force, F measured in newtons, is equal to the voltage times the Q, which is the charge, divided by the distance. So we know the voltage is 6.24. We know that the charge on an electron is that. If we knew the distance, then we could work out what force it is. Okay, so if we come to question 2, what direction is this force? Well, this here is an electron. It's negatively charged, and we know the rule, opposites attract. And so the direction is going to be towards the right. Now question 3, does the force change depending on where the charge is inside the electric field? This is a really common exam question. A lot of students think that because it's this D here, that yes, force does depend on where it is in the field. In fact, that's wrong. Okay, when we look at what electric field strength is the voltage divided by the distance. The voltage across the two parallel plates divided by the distance separating them. This distance doesn't change when the electron comes over here or to over here or to over here. Okay, so does their force change? No, it doesn't change. So how does all this relate to question 3b? Well, so far what we've said is that when an electron moves through a magnetic field, it experiences a force to the left, which is exactly the same as a conductor with 3 electrons on it moving through in a magnetic field. Electrons experience a force to the left. However, when we get the separation of charge of negatives and positives, okay, we create an electric field. And the electric field goes from positive to negative. But if we put an electron down here, that's going to experience a force that way. And for merit, that's the answer. That a conductor with 3 electrons moving through a magnetic field, the electrons will experience a force to the left and positive charges to the right. The separation of charge will create an electric field. And then the electron will experience a force as a result of the electric field as well as of the magnetic field. Now, if you said something like that, that's with merit. But hold on a second. Don't you need a voltage to make an electric field? Okay, so let's look at question number 4. How much potential energy does this little electron have for sitting on the negative plate and it wants to go all the way over to the positive plate? Our formula sheet here says energy equals the electric field strength times the charge times the distance. Now, if I bring this E from up there and replace it with this E over here, because that E is electric field strength and the E is electric field strength, I get volts divided by distance times charge times distance equals the electrical potential energy that my little electron has over here. Now, this equation looks a little bit crazy, but do we notice something? There's a D on the bottom and there's a D on the top. Okay, and so it simplifies down to electric potential energy equals VQ. Now this formula here is actually the definition of what voltage is. Voltage is the amount of energy a group of charge has. So if I said that 1 volt equals 1 joule of energy per 1 coulomb of charge. Okay, so simply by separating electrons, we actually create a voltage. And that sort of makes sense, doesn't it? Because work is being done to separate the charge, where work equals a force times a distance. Okay, so there's a force being applied to the electrons when they're in a wire and they're being moved a distance, so work's being done. So that's just like when you apply a force to lifting something off the ground. Okay, you're applying a force and you're moving a distance, and now it's got gravitational potential energy. It's the same idea when you're moving a wire through a magnetic field. Work's being done to pull these electrons out of the wire and down to one end. Okay, just like lifting a piece of wood off the ground. These now have potential energy. Okay, these charges now have potential energy, and we call that a voltage because it's the amount of potential energy a whole bunch of charges has, and that's a definition of voltage. So simply by moving a conductor through a magnetic field, you're essentially creating a voltage, and it is that voltage that makes the electric field. But can we keep separating charges forever? If we leave our wire moving through a magnetic field for long enough, can we make an infinite amount of voltage? But let's come back to the question at hand in order to be able to answer that. So we're asked to explain in detail what happens to the electrons and discuss all the stuff about forces. So there's 2 forces at work. The first one's from the magnetic field. An electron travelling through a magnetic field will experience a force to the left, and we said that that force was F equals BVQ. And we've said that this force creates a separation of charge, electrons to the left, positive charges to the right, and those separation of charges create a voltage and create an electric field. And that electric field then creates our second force, which is F equals EQ. So let's summarize. When a conductor containing free electrons moves perpendicular to a magnetic field, conductor meaning a metal moving at 90 degrees to the magnetic field is going into the page and the wire is going down the page. So they always have to be at 90 degrees, otherwise this doesn't work. When a conductor containing free electrons moves perpendicular to a magnetic field, the electrons experience a magnetic force to the left as a result of F equals BVQ, magnetic field times velocity times charge. The electrons want to go to the left, and the positive charges experiences a force to the right, and this causes a separation of charge. We have negatives there and positives there. This separation of charge induces a voltage and creates an electric field along the wire in the same direction as the wire, from positive to negative. This then creates an electric force, so F equals EQ, so there's a force on the charge. As opposite charges attract, the electrons will experience a force in the opposite direction to that experienced from the magnetic force. Magnetic force pushes them to the left, electric force pulls them to the right. In this question, the electrons will experience a force to the left due to the magnetic force, and will experience a force to the right due to the electric force. So, if you gave that answer, that's worth an E7. For E8, for the top excellence, you need to explain the answer to our question. Can we keep separating these charges forever? Well, I've already said that F equals EQ is the force to the right, and this is the force to the left. And we'll be able to stop separating charges when these two forces are equal and opposite. I.e., when F magnetic is equal and opposite to F electric, when BVQ is equal and opposite to EQ. Now we notice in this equation that something similar in both. We can cancel out the charges. So when magnetic field strength times the velocity that that charge is travelling at is equal and opposite to the electric field strength, that is when you'll stop being able to separate charge. So can you continue separating charge forever? No. That'll be at this point here, when these two are in equilibrium. That's when you have the maximum induced voltage. So to get E8, we simply need to add this last line. The forces causing the charge separation will continue to act until the magnetic force is equal and opposite to the electric force. So the magnetic force, BVQ, is equal and opposite to the electric force, EQ. The Q's cancel. We've got magnetic force times velocity is equal and opposite to the electric force. We don't actually need mathematics in there for the E8, but it helps to be able to understand what's happening.